So the next talk is by Antti. He wanted to talk about the types of problems with how the heart bug was found, and we're really happy to get more insight on that from the horse's mouth, so to speak. So for the next talk, Antti.
Okay, I'm Antti Karjalainen. I work with Codenomicon. I'm working as a test tool developer. We are developing fast testing tools for different network protocols and file formats. And I'm going to talk about technology behind or methods how the heartbleed bug was found. It's about our track. I don't know how Google did found that, because the heartbleed bug was independently discovered by us and Google. First, I'm going to start with brief introduction to fuzzing. I'm going to introduce different fuzzing methods and failure modes that have been normally or has been catched by fuzzing. And the next part of my talk is about augmented diagnosing methods. It's about what more we could detect, what different problems we can detect from the system under test that are triggered by fuzzing. And in the third part of my talk is demonstrations about how we found the heartbleed bug, and also about GNU-TLS certificate verification bug. Like Sergey said that this year has been quite an awful year for TLS protocols for stupid errors and mistakes. I'm going to show two of those. Okay, I think quite many of you already know about what fuzzing is, but it serves as a good introduction to the other parts of my talk, so here it comes. So fuzzing is negative testing technique. So we are feeding the system under test with invalid and valid data and try that way to get that target system to crash or expose the bugs in the system. So what can be fuzzed? Network protocols, file formats, user interfaces, APIs. From the security point of view, those interfaces that are exposed to or that are crossing the trust boundary are the interesting ones. Of course, user interfaces and APIs should be fast also to get they more robust. But on my speech, I'm going to mostly talk about fuzzing network protocols. Fuzzing does not require access to source code, so you can actually test. It's black box testing method, so you can test also proprietary software. And of course, when you are fuzzing, you can always invent new input. So what's the problem there is to find meaningful test cases and that kind of, for example, boundary conditions that are likely to trigger problems in the target system. These kind of values are, for example, some control strings and overflows or things like that. Most simple fuzzing technique is purely random, so you just dump random data to some network port or file and let the target system pass that. So it's quite shallow testing technique because most systems nowadays are at least that reliable that they don't crash with random data. The little bit more better fuzzing technique is mutation-based fuzzing or template-based fuzzing, where you are having template files or protocol data units or messages, and you take these templates and then fuzz that structure and inject that into the target system. So in that method, the quality of test cases heavily bases on the template files, because it is not possible to generate other functionalities of that protocol which you are not putting in those template files or messages. And also the effectivity depends heavily on protocol or file format. So if there are, for example, lengths or checksums, and you are just fuzzing a template file and those lengths are not calculated over the, let's say, overflow anomaly, then it fails to the length parsing, and that's it. But it works, for example, let's say HTTP, where the message structure is quite simple. There is just these line feeds in the end of the lines or headers, and then there's payload. So you can basically just fuzz those templates files and send them, and it's pretty effective. I don't know if you can see anything about the picture, but it shows something. Then what is the most advanced technique to fuzz is to have an actual protocol implementation, that you are having model of the protocol, that's the syntax, and then you have the rules, the semantics of the protocol that, let's say, calculates correctly lengths over those anomalized values and injects them to the target system. So, and that model-based fuzzing is created from the specification, or that protocol model is created from the specification. So there's no limit in that. You don't need the template files for including all possible HTTP headers. So it can generate those headers in the test cases, and that way it is more efficient. And it also allows for the fuzzing of complex protocols. Let's say TLS. You have to complete the handshake to actually inject to application layer data, for example. You have to make sure that these first steps are correct, so you can actually inject that anomaly to the target system. And of course, because the fuzzer has the data types and knows the value domains of them, so it can try the boundary values, and it knows what are illegal values for the different data types. There's a snippet from session initiation protocol in augmented Bacchus-Naur form. Well, that's the syntax from a little part for the SIP. In addition to this kind of syntax, you need the rules, which, let's say, for example, well, there isn't any complex length or some checksums, but for example, if there were, then you need to calculate those checksums correctly and then get the anomalized value to the parser where it actually is parsed. So what is the anomaly coverage of the data where model-based fuzzer is that we can anomalize field level, put for example on some username field overflow anomaly or things like that. Or the next step is structural. Let's say we have X509 certificate file. We can take a copy from the subject field and add that, for example, 50 times and calculate the ASN1 pair lengths correctly, so that parser really passes also all those 50 subject fields. Then there is sequence level anomalies. For example, on TLS, we could, for example, in the middle of the handshake send client hello again, or things like that. So it messes up with the system under test's state machine. So what can we find using fuzzing? Most obvious is crashes. Then there is denial of services, exposures. All those things are quite easy to see, actually. The target system isn't anymore answering to you, so you know something's messed up. Here's an example from the X509 certificate. So, as you can clearly see, in the beginning there is a length field. So let's say we have a template-based fuzzer and we fuzz a field here. And if we put there extra data, then this length there isn't correct and the parsing would stop in too early. It wouldn't go to the actual anomaly. So you need to have a model-based fuzzer to fuzz X509 certificates. Traditionally, the failure modes that has been recognized using fuzzing has been, well, of course, crashes and memory leakage and denial of service situations. And recognizing these kind of failures is quite straightforward. So you have an external monitor which is monitoring the system responses. If it doesn't failure, if it doesn't respond, then it has crashed. And of course, you can analyze the logs of the target system. If there is some error codes or something like that, we know that our fuzzing has caused something problems there. Then simple network management protocol that can be used for monitor, for example, memory consumption or CPU utilization. And wall grind or address sanitizer builds can be used for detecting, let's say, references outside of the allocated memory or double freeze and problems like that. But what if fuzzing is causing that kind of failure modes that cannot be recognized with an outside monitor? What if the SUT is acting correctly? It doesn't leak memory or does not produce any error messages, but still behaves somehow wrongly. Well, state away fuzzer knows what it has done, and well, the first question, how should the SUT react to the invalid input? Then that is more of a conformance testing problem, but the second one, what are the things that the system under test should not do in any case? And let's say we are fuzzing, for example, user credentials. Then we are knowing that this isn't valid value for the user password, so we shouldn't get to the protected resources. So there comes these augmented diagnosing methods. The kickoff for that development on us was when we were developing our Internet Key Exchange IKE test suite, and we were testing the interoperability against StrongSwan, and we were using RSA signatures for authentication, and everything went fine. We get the test suite to interoperate against the StrongSwan, and we made a beta build and sent that one to some customer. I don't remember what one, and they said that we are calculating the signature in a wrong manner. It doesn't interoperate against their system. Then we were thinking, what's wrong? It works fine against the StrongSwan, and we were studying the problem and noticed that when there is prefix zeros in the signature, StrongSwan actually gives a failure code in the signature verification process, and the method or function which was calling that verification process noticed that, okay, we didn't receive a 0, which is a fail signature. We receive a true, so signature is good, and it proceeded. So that made us to think that if it's possible to test automatically this kind of vulnerabilities, because we are knowing when we are anomalizing for let's say RSA signature, and we know when on that protocol sequence we are requesting for the protected resources, and if we are actually getting those protected resources, then we should give a fail verdict. That's how authentication bypass check was done. So we are anomalizing user credentials and trying to access protected resources without credentials. Apple's go to fail was similar problem. There, this proof of possession signature was not verified correctly, and the Apple's TLS implementation let unauthenticated user to the protected resources. There is a diagram. That's quite simple. The next, this kind of check, this is derived from the authentication bypass check. This is for certificate verification. The problem there is very similar than the authentication bypass. Certificate verification process is quite complex. There is subject's certificate and its private key, and then there's CA's private key and certificate, and CA has signed the certificate, okay? And when we are receiving a certificate, we need to verify that that certificate has been issued by a trusted certificate authority. And this is pretty much what Meredith was presenting yesterday, that this is a complex process, and if security libraries are leaving these things for the application layer developers, then we are in problem, because there is so many steps where you can screw up. The steps are, you need to verify the CA signature, or if the subject certificate isn't signed by the subject or root CA, you have to verify the complete certificate chain to the root CA. You have to check the signatures. You have to verify that certificate subject is the expected one. You have to verify validity period. Check that certificate hasn't been revoked using OCSP protocol. If the used key length is acceptable. Nowadays, some systems doesn't anymore accept 1024-bit long RSA keys, for example. And then, of course, you need to check that the certificate that the other peer is offering you is used for that purpose, that it is used in that sequence. And after all these steps, you know that the certificate is trusted. But after that, you need to verify that the certificate is actually from that party that has sent that. So that other party needs to send a proof of possession using its private key. And if the signature can be verified using the certificate, then we have actually authenticated the other peer. So how do we test certificate verification? Negative testing is, of course, necessary. We need to try invalid values. We need to try, for example, let's say the certificate has been isn't anymore valid, or validity period has expired. And when you are fuzzing the validity period and the signature is calculated over that certificate, then actually the fuzzer needs to have the CA's private key so it can sign over those anomalized values. So that, because the target system first, it checks the signature on that, and if the signature check fails, then it drops the certificate, and we don't know if it checks the validity period. So on a state-aware fuzzer, we need to have a root CA which signs those anomalized certificates. And when we know that there is some problematic values, we can actually give a fail verdict when the system under test accepts those anomalized certificates. Then the next possible step or check is, this is totally different than the last two, those authentication bypass and certificate validation checks. This is amplification. On UDP protocol, it is possible to spoof the sender IP address, and when you spoof that to the distributed DOS attack target's IP address, you can rely that UDP datagram to the victim system. And when there's this kind of UDP protocol which sends larger responses than the request was, it is possible to amplify the sent datagram and so make the distributed DOS attack more severe. There will be more data sent to the target system. So we can check on UDP-based protocols that when we are sending a first message on a sequence, So if the response is bigger for that request, then amplification is possible. And also, anomalization may cause that, for example, on UDP-based protocol, the target system responds with some kind of large error message to the anomalized message, so you get a bigger amplification with the invalid request. This check is derived from the amplification check. When we had done the amplification check, we thought about that. Is it possible to check for unexpected data or bigger responses also on other protocols? Let's say, for example, on TCP. If we recognize that the target system is sending more data that it was received on the valid case, then we can give a warning and for the user and that check what the SUT is sending to you. Is there anything that shouldn't be there? And that was actually the check that notified us about the heartbleed bug. It works like this. On valid test case, we take the reference values, how much we have sent the data and how much we are receiving data, and comparing they simply to the anomalized test case, we can raise the warning or fail verdict and notify the user. So how the heartbleed bug was found then? While we are implementing new test suite for different protocols, we usually test the interoperability against open source systems. And when you do that and you crash the open source system, you want to make that better. And so testing of those open source implementations comes as a byproduct. And last spring, we were developing our TLS fuzzing tools, and we were implementing those, we call them safeguard checks, those four, which was the example, once were these kind of safeguard checks. We're implementing those on the TLS test tool, and I had been working on TTLS protocol before, so I knew the heartbeat protocol from there, and I thought that, hey, TLS supports also the heartbeat protocol. Let's add this also on our TLS fuzzing tool. And we were using OpenSSL 101F and GNU-TLS 3.2.12 as a test targets when we were developing our fuzzer. This is a TLS session. First, there is a TLS handshake, and when the handshake has been completed and the ciphers are up, then the user sends, or client and server sends application data, and you can during that session send heartbeat request, and the other peer should respond with the heartbeat response. The heartbeat protocol is symmetric, so for example, server could send the heartbeat request, and the client should respond with the heartbeat response. And when the session should be closed, then the closing party sends a close notify alert message, and the other peer responds to that. Heartbeat protocol, well, like I said, TLS and DTLS protocols both support it. On DTLS, it is used for figuring out if the other peer is still there, because DTLS works on top of UDP protocol, and you don't actually know if the other peer still listens to you. And on TLS, it is used for keeping the connection alive, so that the timeout counter didn't expire or things like that. So I think it's more appropriate with the DTLS, because usually when you are using TLS, you send some HTTP request and get the response and close the connection, and that's it. You don't actually need to use any heartbeat messages there to test if or keeping the connection alive. And what's quite important aspect is that the use of the heartbeat extension should be negotiated during the TLS handshake. So, for example, a client should say on the client hello that it supports heartbeat protocol and wants to use that, and server accepts it by including that heartbeat protocol extension in the server hello. So I'm showing now you to demo about the test case that raised our awareness about the heartbleed bug. I'm having a vulnerable OpenSSL server here. That's the reference implementation provided along with the OpenSSL library. Like I said, we were including the heartbeat protocol support to the TLS. Oh. And the test case that triggered the problem was this kind of. That's actually a client alert, and the valid client alert looks like this. Let me show you. Content type on there is 1.5, and on the payload inside that record structure is 2 bytes. Alert level, it can be warning or fatal, and then there is this alert description. And those values or fields are on the client alert. They are 0.1 and 0.0. And what was the test case was that we were anomalizing the content type of that client alert. So it was a 1-octet anomaly. Very simple. We had teach our fuzzer to put a heartbeat protocol content type on that field, and it tries that value then. So when we, let me say, I need to have also the valid case for the reference so that it can notice that we are receiving unexpected data. Okay, and our safeguard checks notified that we are getting some unexpected data for the client alert. And let's see if I have the, okay, I have Wireshark here listening to that port, and we saw here that, like Wireshark shows, that it isn't actually anymore a client alert message that we are sending. It is heartbeat request, and what the vulnerable OpenSSL was sending us, it was a valid heartbeat response. And then when we were studying the heartbeat protocol, the message structure is like this, like Sergey was presenting on his presentation. There is one byte type, and then there is 2-octet long payload length. And on that client alert, we had an octet of 0.1, which is basically heartbeat request, and that 0.0 matches with the first octet of the payload length. And what happened is that it reads the second octet for the length on its memory and dumped us the response with that amount of data. When we tried several times, let's say there is 101 octets received there. If we try the same test case again, we are seeing that we are now receiving 245 octets. Okay, so the second octet of that length field is bigger now. So that made us think that we should try using a real heartbeat request with the maximum length. And let me find. So we created a custom anomaly case for that, and it looks like this. So we are having a payload inside the heartbeat record of 3 octets with maximum length there. And when we try to run that against the OpenSSL, we received 64 kilobytes response, which looks like this on Wireshark. There is quite much uninitialized memory dumped because there isn't that much traffic on that my target system. But anyway, there was also some snippets from certificates and so on. So we knew that this is extremely bad because it is actually used memory with which the target is dumping. And of course, the first fear was that if the target system is compromising its private key, because it needs to use its private key to go through the handshake, because it needs to prove that it is the holder of the certificate. And like it was later proved that it really leaked also the private keys. It was using those primes. I think what most people who were claiming that nay, it isn't leaking private keys was actually searching for some ASCII armored presentation of the private key or stuff like that. But actually what you need to look for is primes, and you need to know the architecture of the server, so you know actually the bit presentation and things like that. But testing is quite easy, because if you know and as you know the public key, you know the modulus, and it's a simple calculation of divide, and just using some or scrolling the window of the key length across that 64 kilobytes and doing the attack time over time and testing like that. When the divide goes, it matches. It doesn't produce any leftover, or how do you say that? When the dividation goes okay, you know that you have found a private key. So that was the Heartbleed bug. Another demo is for the GNU-TLS, which was also this spring. Was it like February? GNU-TLS was having this certificate verification bug. Pretty much the same problem as there was with the Apple's Apple's go to fail bug. The Apple's bug was about the proof of possession signature, and GNU-TLS had problems with verification of the CA signature in the certificate. And test cases here. I'm going to shut down the OpenSSL. Okay, so valid signature in the certificate looks like this. It is 256 octets long, and we are going to anomalize that. Let's take that one first. We are going to use or do an underflow anomaly there. So it is only 7 octets long, that signature. Let's see what happens. Our fuzzer is acting now as a malicious OpenSSL, malicious TLS server, and we have vulnerable GNU-TLS client. And when we try against that, it says that handshake has failed. There was an error in the certificate, and the signature was invalid. But let's try a different kind of anomaly. This underflow erases the whole signature, and when that one is sent to the target system, the handshake is completed. So it fails to actually verify the signature in the certificate. And when you think about that, on 2014 there are 3 big TLS implementations: GNU-TLS, OpenSSL, and Apple TLS, and they all are having this kind of very severe vulnerabilities. It was quite eye-opening experience, because what I had thought earlier, that when you are really gonna find something new in the TLS implementation, it's going to be something really difficult, that you need to have huge amount of calculation capacity and so on. But then there is this kind of stupid things, that you fail to verify those 2 signatures that means everything on the TLS. If you fail to verify those signatures, then TLS is merely a layer of obfuscation when doing the man-in-the-middle attack. So it's quite unbelievable. Why don't people test their stuff? And we are still having time, so I saw an example about the amplification. This isn't that bad bug, but it works as a proof of concept for the amplification check. I'm running GNU-TLS TTLS server here. And like I said, TTLS works over UDP protocol, so it is possible to relay those UDP datagrams to the target which you want to denial of service attack. So what we are doing here is that we are sending this kind of anomaly. The record is actually only 1 octet long. run these against the GNU-TLS DTLS server, we notice that we gain the amplification warning. Now let's see here. We are sending only one octet to the target system, and we are receiving a valid hello verify request from the target system. So there is actually amplification of 44 times. We sent only one and received 44, so it is possible to amplify 44 times more data to the target system. But of course, if you calculate their IP layer and UDP layer, then there is overhead and the amplification isn't that big. But anyway, it works as a proof of concept anyway. And it's GNU-TLS reference implementation, so it isn't that bad. But anyway, that was it.
Thank you, Ken.
There's also some questions for you. It's mostly about, do you know where you have deployed the OpenSSL? Please check your stuff and patch your stuff.
So how many more anomalies have you found that you're still researching on? You found more stuff that you have a full list.
On TLS.
Yeah, you have a full list.
I say that we're doing ASAN builds of, let's say, OpenSSL or GNU-TLS. You find every day new vulnerabilities there. So there is problem still.
Yeah, there's a lot of problems. And you have a research list then? Do you have a research list that you're going through?
No, because as I said, it's actually a byproduct. We are trying to develop our own tools. We haven't got that much resource to test the target systems. So what we are doing is to provide our tools for open source projects so they can test their systems on their time, and we don't have to use our time to test open source systems. So it's better to do that way.
Yeah.
And of course, when they are using our fuzzers, they are testing also our systems. And
yeah, we don't seem to have a microphone anywhere around here. I don't know where they went.
it was there.
If you have a question, Sergey, maybe Antti can repeat it.
I'd like to go back to the definition of amplification.
Okay.
Because it's a very interesting model of what the computation does. Because you're forgetting what the content is.
Yeah.
Right?
Yeah.
You just look at the amount of data there.
Yeah.
Right?
Yeah.
But say in some cases this is supposed to happen, right?
Yeah.
So how do you distinguish in the definition between the case when this is supposed to happen versus not?
Well, it doesn't matter if it's supposed to happen. If that does amplify, then the distributed relying denial of service attack is possible. You can spoof the source address. So what actual implementations, for example, DTLS there is having, they are having extra message, hello verify request, which is quite small compared to the normal TLS handshake where the server is actually sending back the certificate and large messages like that. So it is for preventing big amplification there. It sends back the relatively small hello verify request, and if that receiver there is answering to that we know that it's the actual, it doesn't do the relying distributed.
Right. So you model the protocol in terms of lengths of response requests and responses. Because you see, I was thinking that if you were to derive that model automatically, right, then a typical HTTP request, I mean, usually it gets back more data than
but
sent.
it isn't that good check on TCP because, like you said, HTTP, you send a relatively small request and you get the whole website back, so it is meaningless there. But on top of the UDP, it is always possible. If the first response is bigger than the request, you get the amplification.
I see. So it doesn't work for streams, but it does work for datagrams.
Unreliable channel, it is possible.
Right. Well, thank you. That was very interesting.
Do you have more questions? No? All right, in that case, thank you very much, Antti.
Thank you.
And